moirés heterostructures. Thanks, Leni.
Okay. Okay, so well, let me start thanking the organizers for putting together these wonderful conferences and giving me the opportunity to not just only present in my work, but also meeting the great work that people here is doing, and that sometimes in Europe we don't have the possibility to know. So I'm going to introduce you a bit to the field of the correlated states in graphene moiré heterostructures, and I hope that after this you have the impression that I have that is an extremely exciting field, that it started 5 years ago and it's really growing extremely fast. So the particular calculations that I will present, I've done them in collaboration with María José Calderón and Anus Ridata, both at my institute, ICM and Física, and with Alberto Camhaji from Universidad de Buenos Aires. So, well, I will start just with a very brief introduction to the field of correlated electrons, which is, well, what it has taken us here to the conference. So, well, we all have studied at the university that if we want to describe a material, the basic building block is how is their bond structure. So when we are doing this, what we have in mind is that we have electrons which are moving on a background and a potential, a periodic potential, which is created by the atoms and a bit also by the other electrons to some extent. But somehow we think on this on a static potential. And, but of course, electrons repel each other. So what we can expect is that if an electron moves, the state of the other electrons is going to be affected to some extent. In fact, this happens, but most of the time we can consider that, so we can introduce this effect of the repulsion between the electrons in just as a small modification of this band structure picture. So we can introduce that in most of the cases, for most of the materials, as a perturbation. So what we are going to find situations is that, well, the mass of the electron, the effective mass that gives the band structure is not going to be exactly the same. It's going to be a bit larger, or something that we are going to find is specific dependent on, so we are going to define sometimes the fact that the electrons like scatter each other and give a quadratic dependent of the resistivity on temperature. So there are different type of behaviors that we can include in this perturbation and are very well understood. Another possibility that it may happen is that, well, this effect is not perturbative, but that we really have a phase transition and we have some kind of electronic order state. In some cases, this phase transition, even if it really breaks the symmetry of the system, it just somehow alters the band structure in a small range of energies close to the Fermi level, which are the first excitations that we can create. Okay? So then normally in these situations, we talk about some band instabilities because so it's important how is what is happening very much at the Fermi level of the system. Now, there are other systems in which the effect of these electronic correlations is even much stronger than just to produce a phase transition, which is already a lot. Situations in which really all this band picture that we have here can be really very strongly altered, giving not only a phase transition, but also even well, a real strong modifications that, for example, alters, like even in the absence of symmetry breakings, alters this dependence of the resistivity, or even it's able to localize the electron systems that were expected to be metallic, become insulated just due to the localization. What is important in order to know so there are many things many effects that are going to determine how is the effect of the electronic interactions on a system. Particularly, what is going to be important is how is the kinetic energy of the electrons that is going to be given by the bandwidth, by the width of the bands close to the Fermi level, sometimes also very close there, and the electronic repulsion. This electronic repulsion is not just normally the one that we see in the in vacuum, but really it's modified when we are in a solid. And so, of course, as higher is this ratio, we expect that the electronic correlations are going to be stronger. But there are many things that can be influenced, such as the number of carriers that we have, the dimensionality, whether the lattice that we have in our solid is frustrated or no, whether we have screened interactions or they are like the Coulomb 1/R. So whether we have we play in our system with pressure, magnetic fields, or even, for example, if our system is described as a multi-orbital system. So there are different parameters, there are different factors that influence, and as a consequence, we are going to have different quantum phases. The behavior here is very, very rich. So we can have magnetic states, ordered magnetic states, states in which we have magnetic moment, but they really don't give long-range order. We can have systems which are modulations. We can break the rotational symmetry. There are many different possibilities. One state that is going to appear here in the talk is, and I will discuss, is the one of the mode localization. In the mode localization, you can see here the simplest example. Something that is going to be key is, of course, this ratio between the potential energy and the kinetic energy, but also the number of carriers that we have is, in particular, is going to be important that we have an integer number of electrons per side. So imagine a situation in which we have, imagine this is one orbital in a system, a side, in which we can put one electron up with a spin up and one electron with a spin down. And then imagine that we have one electron per side. So if the hoping, so let's say the kinetic energy, is going to try to make the electrons to move from one side to another. And however, now imagine that we have a kind of interaction in which if two electrons are on the same side, this causes a repulsion U. So then this makes that, well, if electrons are jumping and hopping from one side to another and they meet on the same side, this is going to cause a lot of energy. So then if this U, this interaction is very large as compared to the kinetic energy, at some point the system will consider that it's not energetically interesting to be metallic. So in this system, we will have expected the system without interaction to be metallic because if we have a band, this is going to be always partially filled. So we will be in the middle of a band. So interaction is really able just to localize and to kill the transport, okay? So now, this is, so this type of physics is able to give a very rich behavior depending on which system we are, very rich possibilities. Here you have the phase diagram or some type of families that have been studied a lot. So these are the high temperature superconductors based on copper. We have been for more than 35 years trying to understand them, and we really don't understand them yet completely. We have learned a lot of things. These are not the second family of high temperature superconductors here. This Hund coupling that makes that the spins of electron order in an atom, it plays a very important role. We have we have heavy fermion systems in which there are some electrons which tend to be more local and some others that tend to be more itinerant, so the effect of the interactions is different for them. Or we have here some other organic superconductors. What you can see in general is that the phase diagrams are very complex. They have different phases that we can tune just simply changing a bit doping, magnetic field, or pressure. So there are really give this rich behavior. And in some cases, in many cases, in fact, we find superconductivity. Superconductivity, which is normally unconventional, so it's not like the BCS superconductivity that we learned in our solid-state course normally, in which is due to electron-phonon interaction. So normally is that the repulsion is believed, the repulsion between the electrons is believed to be at the heart of the pairing between the electrons. So recently, there has appeared a new type of extract. So far, all these materials that I have put here, they have the idea of the materials that we have. So these are, let's say, you see here the unit cell of the material has a few atoms, okay? Now, recently there has appeared within the field of two-dimensional materials a new type of system to study the strong correlations. So I think that probably most of you or all of you have heard about graphene. So this is a layer of carbon atoms. So it's a honeycomb lattice, okay? And so here, this has been really key, a material really key to study physics of two dimensions, to study what happens when we have a Dirac dispersion, so which is linear dispersion at the, in the bands, or it has many applications. In this system, there are some effects of the electronic correlations, but by itself, graphene is not what we will call a strongly correlated materials. So normally is discussed mostly just with using the band structure, even if what I say there are some effects. Now, there have been many efforts to make graphene a superconductor. This is the wonder material, and superconductivity is normally the property we are all very excited about, particularly what I say, the unconventional superconductivity, but it had not worked for many years. After graphene was exfoliated, people started exfoliating other materials, and also to consider the possibility to really make engineer materials, just putting different materials, layer materials, one atomic layer of one material on top of the other, and in a kind of Lego of 2D materials. But there is also another possibility to engineer materials in which it is to create what is called a moiré heterostructure. In a moiré heterostructure, for example, you can see here is the one in which it's, imagine you put two layers of graphene, and you rotate one of the layers with respect to the other one. And so you create this very large unit cell. You see that you here have a pattern that has a unit cell much larger. And then this is the moiré. It's called moiré because due to a French type of textile that it was called moiré. And then what is going to happen is that this new scale here, this new very big unit cell, is going to control many of the properties of our system. And so, well, so these more heterostructures is what I'm going to talk about. So more than 10 years ago, there was a prediction by a couple of groups, is that, so if we have these two layers of graphene, one rotated with respect to the other one, and we rotate them just 1 degree, okay, so they're almost stacked one on top of the other, just 1 degree, then what they saw is that, so the bands here at the Fermi level, close to the Fermi level, they can be extremely, extremely narrow, okay? So you can see here more or less here. So then what this means is that because they are so narrow that people normally call them flat, even if they are not absolutely flat. So then this means that correlation effects can be important. We can expect that correlation effects will be important in these systems. And so the real excitement started in 2008 when Pablo Jarillo at MIT, so he prepared this system. Well, he has prepared the system a bit before and did some measurement. But in fact, that year, he published that, he put this twist bilayer graphene, so this heterostructure, rotated 1 degree. So normally this 1 degree or 1.05. It's called magic because it's where magic is where you have the flattest bands. And then they put them in between gates. So what makes that you can change the number of carriers in your system. So you can dope the system. And then he measured the resistivity. Okay, well, here there is the conductance. And what he saw, it was surprise. So these are the bands of the system, okay? And so here, in reality, you have two bands, okay? Because there is what is called a valid degeneracy. In graphene, there are two Dirac, so two crossings, and each of them is going to give a kind of these bands. So, and then, so here in this system, you have two bands here, one above and one below. So in these bands, you can have up to 4 holes. So because you have both spin and valley, and in this one, you can have up to 4 electrons. And this here is what is called the charge neutrality point, which is when we haven't changed the number of electrons in our system. So now, what he did, it was he changed the carrier density, okay? And well, first he saw that when he had doped with 4 electrons or with 4 holes, he had a minimum in the conductance here and here. So this he expects. So we expect that because this is a band insulator. Then you can see also minimum here when the system is not doped. This is also that it's not an insulator. It's just a minimum. The system is a semi-metal, okay? We have a Dirac. But then, so somehow what it was unexpected is that if you see here is that we have put 2 electrons or here 2 holes. So we will expect here that the Fermi level, when we do that, is at the middle of our bands, whether the conduction or whether the valence band. So this means that we will be expecting a metal. And what he found is that he had an insulator, so the conductance went to 0. So what this is telling us is that we cannot explain these insulators just with a standard band structure. This is really telling us that the correlations are behind this, this insulating behavior. So the situation was even much more fun. Then there was the explosion when he saw that just also the same year that really very close to this insulator here, he could find 2 superconducting domes. Why was this? Why this created so much excitement? Well, first thing, it was the first time that graphene was becoming superconductor. And somehow the fact that it was close to this insulating state made that it suggested that it could be an unconventional superconductor. We are normally very fan of unconventional superconductors because we don't understand them well. Another thing is that there was similarity in the phase diagram with the one of high TC cuprates, as I will not go into detail, but here we have also an insulator and 2 superconducting domes. In this case, the critical temperature of the superconductor was low, but if we think on the scale of the problem, on the energy scales, it's large. Okay. Another thing is that this is the most diluted superconductor in the sense that if we start from the insulator, going from the insulator to the superconductor requires something like changing something of the order of 1 electron per each 40,000 carbon atoms. So it's really the doping, the change of the number of electrons per carbon atom is absolutely tiny. And of course, also because there was a new, different kind of material in what I'm saying, in the fact that we really have a new length scale of the problem, this very big unit cell. Now, another interesting thing is that these systems are doped with a gate. So they are doped electrostactically. Normally, in cuprates and in most of the strongly correlated superconductors, if we want to dope the system, if we want to change the number of electrons, we have to do a chemical doping. So we have to change atoms. And this introduces a lot of disorder and does not allow to dope too much. So it's quite restricted. So here, as I have told you, we really can add up to 4 electrons or 4 holes per unit cell. So it's really the change is very important. And in fact, this just was the beginning. And when I say it was the beginning, it was just now this is a minimum thing on what's happening, particularly open many new opportunities. Some of them is the fact that, well, twist bilayer, graphene is just one of these possible systems, possible moiré heterostructures. For example, you can do other twist heterostructures with graphene. Like, for example, this is, you have a bilayer which is not rotated, then a twist, and then a bilayer. Or you can have 3 or 4 or 5 graphene layers. So this state that I'm putting here is, they have been all done experimentally. Or you can do a twist bilayer, but with a different 2-dimensional material. So for example, like with this wolframium selenide, but then the 2 layers in the bilayer can be the same material as here, or as in the twist bilayer graphene, but they can also be 2 different compounds, like you have here, okay? And another possibility is that we can also do moiré heterostructures without a twist. Like is just if we put one layer of graphene on top of another material that has a very similar lattice constant, but slightly different, we also create a moiré. So, for example, this is the basic of this tri-layer ABC graphene on HBN. The ABC graphene, these are the 3 layers of graphene, which are stacked one on top of the other. They are not rotated, but they have a specific stacking, so which atom you put on top of each atom. And then if you put that on top of boron nitride, then this makes that, so it has a slightly different lattice constant. And so then this moiré is created due to the different lattice constant between the boron nitride and the graphene. So now, another important thing is that there is an imprisonability of these systems. So we, as I have said, well, we can play with the twist angle, we can play with the substrate alignment, with the type of heterostructure and material, but we can also change the correlated state with the temperature, with the doping, with the gate. We can apply pressure to the interlayer coupling. We can also apply strain and change the system. We can apply a perpendicular field, and I'm going to mention that, so this can be really alter our band structure, magnetic field, or also control the screening. So you can see here some examples. For example, here, they play with the critical temperature, just tuning with pressure. This is twist bilayer graphene. This is a different system. This is a tri-layer graphene, twist tri-layer graphene. So if they apply an electric field perpendicular, so here there is no perpendicular electric field, there is a perpendicular electric field, you can see how these flat bands that we have here they become modified by the electric field, considerably modified. And then when we look, for example, here, one looks at the resistivity, it really changes a lot. Okay, so we really, even here, are able, with this electric field, to control phase transitions. Another thing, for example, this is another example in which just depending how far we put this gate as compared to the our twist bilayer graphene, we are going to also control a bit the interaction in twist bilayer graphene. And you can see, for example, here they are controlling the size of the insulating gap, just making that playing a bit with this screening. Okay? And this can be also done, one thing is with the gate, but also, for example, in this experiment, what they did is they put another graphene bilayer and played with charging that or not charging that. So then people have seen a lot of correlated states now. So at the beginning, I have told you that there was a lot of excitement because they have managed to see 2 correlated states, one with 2 electrons and one with 2 holes. Now, this is the situation now in which they are playing with magnetic field. Here the electrons that are doped per moiré unit cell. And then you can see here we have just huge number of different type of correlated states. And the different colors that you see here is because they are essentially different type of correlated is really the essence of the type of symmetries and some topological properties in these materials, in these correlated states change. So it's really an absolutely extremely rich system. Other, for example, states that have been, and here in twist value graphene, people have observed a lot of different kind of, as I say, of phases. But you can see, for example, here some examples in other systems. Like this is twist double bilayer graphene, the one that I mentioned before. So it's bilayer, twist, bilayer. And you can, here, for example, is a state in which the lattice rotation has been broken. So this should have symmetry, it's 120 degrees. Then you can see here in this tri-layer graphene HBN, they have observed topological phases, for example, what is observed here in the transversal conductivity, or here, for example, is an example of insulators at fractional fillings. Yeah.
How do you decide which of these descriptions correspond to which?
So there is what is called a Diophantine equation, in which they look at the filling in terms of the magnetic field, and so so this is the doping, this is the magnetic flux, and so these are two quantities. So depending which, if these quantities are integer, fractional, zero, so this is the way in which it's decided. So how it couples the flux. Okay, so but it's not just that we have a lot of insulating state or symmetry breaking states. Is that if we go to the normal state, we also see a lot of unconventional behavior. So before I was telling you that the quadratic behavior of the resistivity with temperature was a behavior that we expected when correlations were introduced perturbatively. So for example, so they have observed a behavior which is resistivity linear in temperature. This is what we normally in the field of correlated electrons say that it's an strange metal. Also, they have observed that the density of states change with doping, which is something that you don't expect if correlations are not very strong. So really, there are a lot of different effects that are observed in this system, and the field is really growing constantly. We are getting new and new different effects and states.
So what's the symmetry that is being broken?
No, well, whatever. So is that symmetry breaking? I mean is that, for example, these states, these symmetry breaking states that I mentioned here. So normally they are at low temperatures. So what I'm saying is that whatever effect is happening, if you increase the temperature and you go to the normal state that you will expect to be better behave, what I'm saying is that this is also anomalous. Even when you don't break the symmetry, so the properties of your system are highly anomalous. That is what I wanted to say, is that at higher temperatures than the ones at which the symmetry break is broken, the properties are also unconventional. Yeah. Okay, so now what I'm going to do, I'm going to discuss, so I have mentioned you a bit about twist bilayer graphene. This is what I'm going to talk about tomorrow in the system, like the way in which we will describe this system in the talk. Maybe I mention one or two words about that. And I'm going to talk to you about this system, the three-layer ABC on boron nitride. So this system, you are going to see, here in this system, what we have is, it's a moiré from, that we don't get this moiré from breaking the, so rotating, but from a lattice mismatch. So before going to that, so let me just say a few words to be able to, that you are not lost. So here, normally when we describe the system, it's very often that we do a band structure calculation with something like ab initio method. So in this system, we have 11 atoms per unit cell, more or less. So then normally it's not possible, and then we have to go to simpler methods like tie bindings, things like that. And then, but then also to study the correlations, there are different possibilities. One is to consider an atomistic description, like consider all these 11,000 atoms to describe the system. We can work in K space, or we can work with effective. Imagine that in our system we have like effective atoms, like something which are placed like here at this side or at this other side. So this is the type. So here normally we want to try to have simple but realistic model, and then well, and one of the questions is which is this good model, but this is the framework in which I'm going to work. Okay. Okay. So let me tell you a bit first the idea. So we have this. How is this system? So in this system we have this tri-layer ABC, in which so this is the way in which you see them here. This is the way in which the three graphene layers are stacked one on top of each other. Okay? So then if we put them, we put them on boron nitride, okay, top and bottom, and then we put gates. So with these gates, we are going to be able to control both the number of electrons, the number of currents in our system, and the band structure. So somehow is that what we are doing is that we are applying a perpendicular field, but also changing the number of electrons. So if we don't align our system with the boron nitride, what we are going to see is the physics of a tri-layer. Okay, this is a physics that has been studied to some. It has been studied a few years ago, even if very recently, as I will mention, we are having a lot of surprises also in this system. But now, so if we align this tri-layer with the boron nitride, as I have mentioned before, we had one. The lattice constant was very similar, but not exact, and so then we are going to have a moiré. So what I'm going to say, and what I'm going to propose here is that just putting this alignment, we are going to be able to switch on and off the mode physics, this strong correlations physics. So in fact, so as I said, what the amount of electrons that we are adding to our system, if we think on this number of electrons per carbon atom, so it's a very small amount, okay? So in this system, in this tri-layer, the unit cell is very small. So we will have just the doping, it will be very, very small. So then this means that we are not expecting to have mode physics that I have told you that it was associated to the integers. We don't expect to have that in the system. And so, but here, so with this, creating this heterox structure, we are going to be able to be at integer fillings of these new large unit cells. And so, so what I'm going to look at is at how this mode physics will appear here. So well, this is the band structure of this system. So if we don't apply a magnetic field, so then these two bands will be touching, okay? You see that they are already quite flat. You can see here that here we are at energies of the order of milli-electron volts. Again, we have two of these bands because of the valley in graphene. And in fact, well, this system people observed already in March 2018. They also observed correlated insulating state in this system. In particular, they observed that there has been more experiments afterwards, but they observed that when this valence band that you see here was doped with 1 or 2 holes. And so, well, so then this one, so we will expect to have at least 4 holes to observe an insulator, but then, so then it's clear that these are correlated states. Okay, so now what I'm going to study is, and then is what I say, so we need the magnetic field to have this band isolated. So an interesting thing in this system is that depending on the sign of the electric field, our valence band, which is the one in which I'm going to focus, is trivial. It means that it's not topological, or it's topological. Okay, so I'm going to focus on the case in which the valence band is trivial. Okay, so then we have this band. So this is we can isolate that, and then because we have two valleys, this is similar as if in our system we have an effective lattice, so a lattice of effective atoms, which is triangular here, okay, and in which have these two orbitals, okay? So somehow what we are doing is we are going from this very complicated structure to an effective lattice with, to an effective triangular lattice with two orbitals per side, okay? One thing that is going to happen is that when we describe our system, the hopings that describe the kinetic energy are complex. Zhang and Sentil studied also how are the interactions in this model a few years ago, and they said that they saw that they are of the order for this screening value, which is not very clear exactly which one it is, which one should be. So this is something which in the community still we don't know very well. So they are around 25 milli-electron volts. Then the interaction between the densities at first nearest neighbor, they're of the order of 10 milli-electron volts. And then other interactions that tend to polarize the electrons inside or in neighboring sites, they are also much smaller. So then these interactions, we are going to neglect them. And then, well, if we don't have charge modulation in our system, so the first nearest neighbor modulation in a system simple like this can be effectively, to some extent for the main effects, introduced into an effective interaction U. So what I'm going to do is I'm going to look at the system as if I have an effective interaction U, which is going to have both the effect of the intra and it's going to be slightly suppressed due to the inter, but as I say, this value is also not known. So I'm going to, as I say, I'm going to focus on this valence band, and then so we have I'm going to focus on the case in which we have two holes. So we are close to this, so we are going to be around this insulating state, that is the one that corresponds to holes. And then I'm going to have an electric field, which is this particular value. So you see first that if we don't have, first here, this is the case in which we haven't put any interaction. So this band there, it's going to be that band there. So this is the picture with the one we are going to compare to see the effect of the interactions. Then if we switch now on the interactions, first I'm going to put an interaction which is for this system, it's possible, it's doable, it's not clear, but it's probably maybe a bit large. So somehow what you can see here, as I was telling you before, that the interactions were going to alter our band structure, but you can see this was the original, the U equals 0, and you can see that we have opened a gap, and also is that so this band is not well defined anymore. It's not just that we have opened a gap, but is that this is very, let's say, incoherent, okay? So what is happening here is that we are above our mode transition at this type of interactions. And these are what we call the Hubbard band, which are the ones that appear in the mode insulator. Now we reduce the interaction, and so we are at smaller values. And what we observe is that we have a remnant of these bands here and here, but we also have a kind of remnant. So the system is metallic. We have a remnant of this original band, but it has been it has changed a lot. It's really considerably renormalized. Yes.
How do you reduce the interactions? This experiment?
No, this is calculations. But in other materials, let's say in this type of materials that I have discussed in the cuprates and in system like this, people has observed this experimentally. For example, they observed this with photoemission. With angle resolved photoemission, you can see the bands, and you can see how the band structure for example, if you are able to dope, how this depends on doping, and how this can be different, very broad, and things like that. Yeah.
But the interaction you can't experimentally change.
Okay, okay. So this is, okay, let's say this is, I'm theorist. I'm doing this in the calculation. In principle, for example, in this system, what I was saying is that, for example, bringing the gate closer, I play with the screening. So I play to some extent, or sometimes if you apply pressure, what you do is you change the kinetic energy. Okay, so there is some ways of changing that. In particular, for example, in twist bilayer graphene, people has managed to switch on and off the insulators. So you can see that, well, this band is strongly renormalized, okay? So for this interaction, and so this is already more in the range that we expect. But even if we, for example, go to a much smaller interaction, the effects are still sizable. So what this is telling us is that we do expect to have mode physics at the values of experimental values. Okay? So now, what this is going to make, of course, if we have this effect in the bands, we expect to see a strong effect in the density of states. And you can see here, before I have looked at the integer value where we had the interactions, okay? But you can see here, if we compare the non-interacting density of states with the interacting density of states, you can see that we do also expect to have some effect, a reduced effect if we dope the system, but it's even if we have dope it to this value, which is considerably large, so the effects are still considerable, okay? But of course, they are going to be stronger close to the integer filling. And another interesting thing that happened in these mode systems is that if we increase the temperature, so in many cases, it somehow is that, okay, you increase the temperature and then your correlation effects disappear. So what you can see here is that before I was at quite low temperature, 120 milli-K, then we were having here this band at this interaction. Now we increase the temperature, and we see that our band is kind of completely gone. So you can see here also in the density of states. So what we see here is that we expect is that at a few Kelvin already in our system, we are losing this coherence band, so this more standard band. So, and then this is going to give a normal state, particularly at that interactions, that is going to be anomalous. So another thing that we can ask is whether this system orders if we allow that. So far, I have not been allowed my system to break the symmetry. Now we can ask whether this can break the symmetry. And in fact, in this type of models and this type of systems, we normally have the tendency to see an anti-ferromagnetic state. So here we have a lattice that is frustrated, so it's a triangular lattice. So it's so then it's less obvious what kind of states that are found. And in particular, what we find is we find an anti-ferromagnetic state at interactions at which the system is really close to this localization and also very close to the integer filling. So what this is really telling us is that the anti-ferromagnetic state that we are finding is associated to this process of this creating this mode insulator. And we believe we cannot really address that exactly, but we believe that the anti-ferromagnetic state that we are obtaining is this ordering in which we are breaking also the symmetry of our system, the triangular symmetry in which we have this type of stripes. Okay? So one thing that we can see is that the order disappears around 3 or 4 Kelvin. And this is, so then we have seen before that at a few Kelvin, we were expecting that our band was disappearing. So what it's telling us is that the normal state in which this anti-ferromagnetic state will appear is going to be very unconventional. So let me say what we really expect. I have told you that what we were going to see is that it was the fact that the confinement was going to create this mode physics. So here in this tri-layer, as I have said, so we will expect, we don't expect mode physics, so we expect to have a band like this, okay, like well-defined, except if we have symmetry breaking, that I will mention now. And so the question is that when we now align with this boron nitride and we create all this confinement, so all this physics that we are going to find here is associated with the fact that we have put this confinement. So then is when we expect to see this mode-like physics. Particularly, well, recently, these tri-layers have been found to be also extremely interesting. Then people have done compressibility measurements in this tri-layer, and they have found that there are a few transitions. Fundamentally, they have this metallic. The tri-layer is metallic. Fundamentally, this system, they have found that there are ferromagnetic states, so ordering of the spins and sometimes of the valleys. So this is what they observe, and here, so here they are playing with the doping, and here they are playing with the electric field, and these changes that you observe. So in fact, here there are different. Here is hole doping, electron doping. There are different phases here, and so later they have put the alignment, and they have observed something which is similar, related to here, but with some insulated states here in yellow. So their proposal, it was, okay, because we already have ferromagnetism in this system. By the way, they also have superconductivity in some regions. Because we also have ferromagnetism, everything is ferromagnetism. Also in the moiré, so they were saying the insulated state was associated to the ferromagnetism. So what we are, in fact, saying is that, so somehow here, close to the insulators, we do expect that the behavior is going to be much more complicated because this confinement is really bringing this mode physics. And in particular, so our proposal is to look at the normal state above from the symmetry breakings, because the behavior, the mode physics, should appear in terms of unconventional doping and temperature behavior. Now, regarding, do we expect to see anti-ferromagnetism? Well, this is not really clear, because if you remember at the beginning, when I was starting looking at these materials, I told you that we were throwing away some small terms of the interactions. So somehow it turns out that these small terms that we have thrown away are of the same order of magnitudes of the ones that are stabilizing our anti-ferromagnetism. So this makes that they are going to be competing. So we cannot say exactly which is going to be the system. Now, something that is very interesting and very exciting is that, well, very recently, there has been a photocurrent experiment in which they have seen some optical transitions that will not be in this. So they have done it in this moiré, in particular at this insulating state, in which they have observed some transition that will not be allowed in a ferromagnetic state, but that are really compatible with being the transition between the Hubbard bands. So just the last word that I'm going to say. So at the beginning, I was telling you that, OK, so we can, so the twist bilayer graphene has been, was compared at the beginning with the cuprate. So somehow, well, for those of you which are used to mode, you have seen that the discussion, the property that I was discussing were have been found in some other mode systems. In particular, what I have done is to map the problem to a two-orbital Hubbard model in a triangular lattice. In this case, as I say, with complex long-range hopping, which are important, by the way, to stabilize the anti-ferromagnetism in the triangular lattice. And in fact, is that with the cuprates, we have somehow a kind of related model. In this case, it's single orbital square lattice, and normally the hoppings are simpler. Now, the case of twist bilayer graphene, what we are going to see, this is for the people in the conference, which I will talk tomorrow, is we are going to see that the description is much more complicated, and in particular, it's closer to a very complicated heavy fermion-like system. Okay, so I think I will just stop here. Thanks.
Thank you very much, Leni, for this very nice talk. We are open for questions. Okay.
Thank you for this very nice talk.
Thanks.
So it's about your two-orbital Hubbard model. Is it spinless or spinful?
It's a spinful.
okay.
It's a spinful, yeah.
Right, so is that why you're allowed to choose complex hoppings without breaking time reversal symmetry?
So, okay, so sorry. We have in each valley, so the two orbital is associated to the two valleys. In each valley, we don't have time reversal symmetry, but the two valleys are related by time reversal symmetry. So then it's where only once we have the two valleys, so I have been plotting all the time only one valley. So once you have the two valleys is when you recover the time reversal symmetry.
But does that mean that your hoppings will now have to be real? Or
in each of the valleys, they don't have to be real. The way in which they come, so they are complex, but that does not necessarily mean that the system breaks the time reversal symmetry. So in fact, this complexity is associated to the fact that you are let's say, fitting a band. So this type of hoppings come from fitting to a band that you have obtained in a way. So normally you start from parameters starting in a continuum model for graphene. And then you have different terms in graphene. And then you do introduce the moirés in some effective way. So you have some bands. And then these bands that you have obtained in a completely different way, you fit them with a moiré, so with a barrier function model. Okay, and it's there from where the hoppings come. But this is what I say, within each valley, there is no time reversal symmetry. But once you have the two of them, they are related. The energies is the energy of one of them is, in one of the valley is the energy in one at K, the other one at minus K. Okay.
Thank you. So you mentioned that you focused, if I understood it correctly, you focused on the trivial band case, but you also could have topological bands. So what kind of changes do you expect for this Mott physics in that case?
So, okay, so the first thing is that I cannot, because if it's topological, the band, I cannot use just take only one band and describe it in terms of barrier functions. So depending on how is the topology, maybe I can take a model with several bands. Sometimes that's possible. So that's the very first thing. So from the experiment, they have managed to see also insulating state. So this is something that eventually we also want to look at also with the topological state. They have also observed some insulated states, but somehow the ones in the trivial band are more robust. So they stay more both in temperature and it's normally easier to see them. So, but somehow the other ones, we haven't studied that yet. It's something for the future.
Yes, so, well, I'm not so expert in the field, so my question will be naive. There was some people contesting the fact that the system was a Mott state. The Mott physics was not so relevant at the end, because if they apply magnetic field, for example, they see the Mott state disappearing rather quickly compared to what
sorry, are you talking about twist bilayer graphene or the ABC?
Twist bilayer graphene.
So, okay, in twist bilayer graphene, that's still very. I was talking about that long ago.
You were talking about it.
So, okay, so one thing.
Well, you are not the only one, actually.
Okay. So one thing is that experimentally in twist bilayer graphene, there is a lot of sample sensibility. Some states, in some states, the insulating states remain with the field, in some other that don't. For example, if I show you, it's uncontrolled yet, the sensitivity to sample in Twist-Valley graphene. So then, for example, at the beginning, I told you that the first insulating states that have been observed were the one at -2 and the one at 2 electrons per moiré unit cell. But if you see here that we have so many insulating states, this one we don't have. So somehow there is, that was in the first experiment, but with this effect of the magnetic field. But later, I have seen also the opposite behavior. And in some other cases, you see here, for example, this one, well, is that this one stays up to very large fields. So somehow there is still, and that's particular for Twist-Valley graphene, this very strong sensibility to sample that is not clear. Where it's coming from, whether it is experimental effect or whether it's something that the system is very, very sensitive. But in any case, as you are going to see tomorrow, is that this, so this system, it's very, very complex. It's the one that we are studying now, and it's very, very complex. Yeah.
There were questions around here? Or not anymore?
Yeah, here there are two.
Sorry, I'm not from the field. Is there a simple, is 1.1 degrees a rational function, or why is that theta special? Can you say?
Well, that's associated to the values. So one can see that is special if you do this type of modeling. But the fact that it's 1.1 or another one depends on the values of the Fermi velocity and things like that. So it's not that it's a number. So it's a number which depends on the parameters of the graphene.
Sorry, but if you continuously change 1.1, then you'll lose the unit. It doesn't grow continuously, right? It just goes.
No, it does not go. In fact, this is the first magic angle. For angles smaller, so it does not, from 0 to 1.1 or 1, it does not go continually. There are several other magic angles.
So that's what. So 1.1 is probably some rational number, right? It's not. I'm just asking.
No, it's not rational. So it can be 1.1. So if I change slightly the parameters, so the Fermi velocity in graphene, instead of 1.1, it can be 1.08 or 1.05, so, or 1.1, or if I introduce relaxation in the system, that changes a bit. So it's something which, so you can write this 1.1 in terms of, is what I said, the Fermi velocity, the parameters of, with the one you described, graphene. And also if there is relaxation or not. If I, for example, in the original calculations, there was no gap here. And then, so this one, in fact, is much more recent. And this one it has been seen to be associated to the fact that you really relax the system, the Twist-Valley graphene. Yeah.
So very nice talk, very interesting. My understanding from these effective models based on Vanier states is that not only the on-site Hubbard term is important, but also first neighbor, sometimes second neighbor interaction terms are important. So can you include those in your DMFT calculations?
So well, in the DMFT, if you do DMFT like that, it's Hubbard. So you can in extended DMFT you can introduce the effect of longer range interactions.
So is it just a single site?
Yeah, this is single site what we are doing. Yeah. But for example, in this one, we are introducing that effectively, like reducing the value of U. But for example, in Twist-Valley graphene, it's much more complicated, and you have to keep them in some particular way, because even at the hat tree level, there is a deformation of the system that normally here, it's something that you absorb in the chemical potential.
Okay, thank you.
More questions? Yes.
This is more about possible perspective for the future. Could you assess the superconductivity with this method? So you have to need something more than DMFT or to orbital Haber model.
So well, let's say for example in more with studying with clusters and things like that with DMFT, yeah. people can study superconductivity and
But
yeah.
somebody tried.
So in other systems, like in the ABC, people have not looked at that. In fact, in ABC, there was, at the time, there was a claim that it was superconductor, but it has not been confirmed. So there is what is called the fragile superconductivity in some of these systems. In twist-bilayer graphene, it has been done with some simple models, which are not very clear, but for example, in cuprates and in other systems, so people have done very nice predictions.
Do we know something experimentally on the order parameter in superconductivity?
Okay, so, well, it's what I say. In the twist-bilayer graphene, so, well, it's believed to be unconventional. There are still really experimentally very few experiments, but for example, they are observing what looks kind of possibility to have nodal behavior, things like that. There is people claiming that there is a pseudo, well, that was in the tree-layer recently, but also, no, also in the twist-bilayer it has been discussed. Also, in some of the systems, but also even in the ABC tri-layer without any moiré, in some systems, so the superconducting states violates Pauli limit. So then people believe that some of these states could be triplet. So, and in terms of theory for twist-bilayer graphene, all kind of imaginable possibilities for order parameters have been proposed.
As people talked about topological superconductivity.
Also, yes, but it's what I say, all kind you can imagine have been proposed. But is that, so still experimentally, there are not so many, but I think it, and there is some people also who claims that it's electron phonon. It's what I say, still is very open. It still is, that superconductivity is still very open, but yeah. But is that, so I think we will see, so the field is really advancing extremely, extremely fast. And so I think that we will know more in the next few years. Yeah.
More questions? If not, let's thank Leni again. And we go for a coffee break. We reconvene at 3:30.
Okay. Pues nada, obviamente no.